Thank you for being here this morning. It's my pleasure to be here. I'm an experimental psychologist and a member of a small and dedicated group of psychologists known as ecological psychologists or Gibsonians. And much of what we have to say is best understood and best described by comparing it with sort of more traditional cognitive science. So let me start with a little overview of what I'm going to talk about today. I'm going to first present a problem for you, a perception-action problem, and ask you to think about how you would solve it to help you decide whether you're, by the end of the talk, more ecological or more traditional cognitive in your approach. And then I'm going to draw some distinctions, 6 distinctions, if you will, between the ecological approach and the more traditional approach. And I'm going to frame that as 6 principles of ecological psychology. The first 5 of these I'll go through fairly quickly, and then the last of them concerns learning, and that's where the majority of my attention will be given this morning. So, let us start with the outfielder problem. Okay, I know you're Europeans, mostly, but imagine you're standing, one can make a football analogy out of this, but imagine you're standing in center field, and a ball is hit by a batter and flies in your sagittal plane. This is the most difficult for a new learner of baseball to catch. Okay, it flies just in your sagittal plane. You're going to see part of the trajectory and eventually adjust your activity so that you intercept the ball. So now the question is, how do you do that? Take 3 seconds and think about if you were to try to explain this as a scientist. Now, this problem has been around for some time now, so perhaps you're already familiar with the ecological approach. But if not, think about what sorts of processes you imagine would take place in catching the ball. The usual response that one sees from cognitive psychologists is that you watch the first part of the trajectory, and that is followed by certain mental processes. I've got this bubble, thought bubble labeled here. And usually the goal of what's happening in the bubble is an extrapolation of the trajectory of the ball. The details of what goes on in that bubble will differ, but you extrapolate the trajectory of the ball, figure out where it's going to land and when it's going to land, and then guide your motor activity accordingly. So what goes in the bubble? Well, different theorists would come up with different things. Processes in the cortex, say, or models of gravity, memory, sensory integration, binocularity, even auditory system, and of course, computation. So the problem then is really divided up into perception and prediction of the future, action planning, and then execution of the action. Now, as I discuss these 6 principles, I'll be sort of describing a different kind of approach, the kind of approach that would follow from the ecological view, and one that would be very different from this characterization that I've just presented. Okay, so 6 principles. The first principle is animal-environment mutuality. And here the claim is that one ought not separate animal and environment in trying to solve problems in psychology, okay? Problems of perception, say. I'm fundamentally a student of perception. And the more common view is of animal-environment dualism, that cognitive psychologists really worry very little about the environment and concentrate on what's going on inside the animal's skin. They therefore tend to describe the environment in animal neutral terms, not sort of worrying, just standard physics. So if you want to talk about characteristics of the environment, you might measure size with a ruler or mass with a scale. And in terms of the information to which your sensory systems might be sensitive, again, let's borrow the metrics from physics. Light is about wavelength, number of photons, etc. The ecological view, in contrast, is going to try to describe the environment in animal referential terms. Now, the most important of these is affordances, and this is perhaps the most famous concept that has crawled out of the ecological view and become a mainstream concept, although I must tell you that many people use it in a way very different from the way Gibson originally used it. And of course, he actually coined the term. But affordances are the actions permitted by some object, event, or place in the environment. And those are animal specific. What this object affords me would be very different from that which affords a child or a squirrel, or at this university, a feral cat. Similarly, in information, we're going to seek a characterization in terms of richer, higher order patterns. We're not going to be bound simply to local luminance levels, but to look for patterns both over space and over time. Okay, so what do affordances look like? What does it mean to measure in terms of possibility of action? A couple quick examples. We might measure an aperture, so rather than simply talking about the size or shape of an aperture, we'd say that that aperture can be walked through. That would be affordance of this doorway. Similarly, rather than talking about the height of a staircase, we might describe it as a step-down place, okay, and not concentrate on traditional metrics like distance. And similarly, a ball might be graspable rather than, or throwable, rather than, weighing 200 grams and having a diameter of, 12 centimeters. Okay, so now as we go back to the baseball batting example, right here, our first principle, animal, environment, mutualism. These two things go together. Let's not separate them. What does that mean for baseball batting? Well, it's going to be that the information, the task, we really want to describe it as about the ball catcher system. It's not about the ball and its trajectory, followed by some separate animal process, like route planning, but instead, the optics that we might be sensitive to might be about your relationship to the ball, and it might tell you exactly what to do to catch it or to intercept it. Okay, let's move on to principle 2, and that is the specificity of information. In the ecological view, it's emphasized that there's a one-to-one relationship between optical patterns or acoustic patterns and objects and events in the environment, or affordances in the environment. And traditionally, psychology and philosophy have emphasized a many-to-one relationship, where there can be any sort of shape out there, and it doesn't tell you about what the distal object is like. It doesn't inform about it. So, for example, image optics best characterizes the traditional study of the light to an eye. Let's look at the characteristics of a retinal image, for example. Ecological optics, in contrast, is going to emphasize higher order optical patterns that are specific to properties of the world. Okay, why is this important? Well, where you stand on this issue of specificity sets the stage for your theory of perception. If you assume that the input is a static, two-dimensional image, a standard retinal image over time, there are various problems with it. Those problems include that it's upside down and backwards. People have worried about that. That size, distance are distorted, and shape. What's meant in this, to be demonstrated in this picture is that, trapezoids and squares that are far away or close up can all yield the same image on the retina, a many-to-one relationship. Now, if that's your starting point, and we know what your ending point is, that you look up here and see me to be a normal-sized person in 3 dimensions, and so I depart in a variety of, your experience of the world departs in a variety of ways from image properties. So this is what your theory is going to have to solve if you start with non-specifying information. How do you get from things like this to things like this? Okay, from the ecological view, and let's now turn our attention back to baseball catching, what we would notice about the optical patterns that accompany this baseball flying at you in the sagittal plane would be that if your eye, and that at point B is meant to be your eye, is at the location that the ball will arrive, if you're already in the right place, the optical pattern that you will see is of a ball basically rising on the image plane at a constant velocity. Okay? So constant velocity, that means you're in the right place. If, on the other hand, you are standing in front of where the ball will land, the resulting optical pattern will be accelerating on the image plane, and conversely, if you are behind where the ball is going to land, the ball will decelerate on the image plane. Okay, so if you're pointing to it, it starts to slow down. So these higher order patterns, if you will, inform of where the ball is going to land. So this presents a very different problem for a theory of perception if you're worried, or a theory of catching balls, than, let's say, a succession of static retinal images. So this pattern of acceleration. Okay, we'll come back to this. But for now, let's turn to our third principle, and that is perception-action mutuality. The history of psychology has been marked by a separation of these, but for the ecological view, perception and action go hand in hand. The point of perceiving is to guide activity in the short term and the long term. Traditionally, though, these activities have been separated. Perception is seen as a process that precedes action, and action follows, and indeed, knowledge and representations become the end point of perception and the starting point of action. From an ecological view, we are going to notice several kinds of relationships between perception and action. For example, the importance of exploration creating information. Okay, you can obtain information through exploration, that our execution will reveal information, and that attending to this conjoint relationship, perception-action mutuality, will make us think about looking for information that in fact guides our action. So now let's put this back in the context of baseball catching. So the traditional dualistic view was the story we saw a few moments ago: perception of time and place of landing, appropriate action planning, and execution. Whereas when you start to exploit optical acceleration, as information, a new possibility obtains. Namely, that relationship that we looked at here holds in a variety of circumstances. It holds if you are standing in the right place. It also holds, in the second case, if the ball is just going straight up and down and you are running at the right speed. It holds if the ball is moving forward and you are running towards it. And it holds, finally, if the ball is going behind you and you are running appropriately. So if we put that all together, this would suggest a way of controlling locomotion in ball catching. Namely, run in such a way as to cancel out this optical acceleration. Okay? That will lead to, if you are successful in doing that, that will lead to an intersection of your eye path and the ball path. So you will apparently solve the problem of where to be and when to be there without knowing either, right? There's nothing about time here, there's nothing about place. It just says, use this style of control, adjust your ground reaction forces or the ground reaction forces that are created proportional to the acceleration in the optic array, and you will get to the right place at the right time. Okay. Our next principle is direct perception, and that simply argues that perception is the pickup of information. And of course, information as defined earlier. The more traditional view, of course, is that perception is an inferential process, computational, and memorial. And in part, that's dictated by this information that we started with, that this insufficiency of traditional stimulus. So because the retinal image is ambiguous, perception must involve these kinds of processes. From our perspective, though, because information is specific to important environmental events, and specific, for example, to how you should be running, then your job is to basically let that information control your locomotion. Not to store, not to compare, not to retrieve, not to predict, not to anticipate, just yield control to the appropriate information. Another key feature of, I'm going to skip that. Another key feature of direct perception is the idea that you sort of pick up information in a single step. And I'm going to just briefly mention a couple metaphors for this, because sometimes it's difficult to intuit what it might mean to just directly measure a higher order property. And a metaphor introduced by Sverker Runesson, a Swedish psychologist, said we should think about perceptual mechanisms as smart perceptual devices, okay? And he used as a metaphor for that a particular smart device. Here's the problem. You want to determine the area of a rectangle. How to do that? Now, our usual inclination is to do the sort of traditional cognitive psychology thing. Measure lower order variables, length, width, and then take out our calculator and do a computation, and we get the result. But in Runesson's metaphor, namely the polar planimeter, you have a device that engages in an activity that will ultimately measure area without measuring length, without measuring width, and without doing computations. Usually, they're used for measuring irregularly shaped objects, and what you do is simply trace the pole end is planted, and then you trace the lens around the perimeter, and when you're all done, you have measured area, and you can read the measurement off the dial. So it measures area directly, without measuring lower order properties, without doing calculations. And of course, we could use it as well to measure a rectangle. Now, notice, however, that if you're sure that the way to measure the area of a rectangle is to measure a length and a height and do a calculation, you're going to be in trouble here because you discover that this device is really bad at measuring lengths. It's, it gets, the dial will move, but you won't have a good basis to start. So a device that measures area measures a higher order property without measuring lower order properties and doing calculations. So think of that as sort of the way an ecological psychologist would think that a biological information detection system works. A second metaphor that I won't describe in any detail, but just sort of mention it here, is of resonance. And what resonance is all about is simply that maybe we should think about cognitive systems working more like radios than computers. Okay. Let's turn our attention now to the fifth principle of ecological psychology, and this I will sort of generally label as a commitment to physical science. And what is meant by that? It's not reductionistic, let me say that to start with. We believe that phenomena in general are to be understood in terms of laws and circumstances, or boundary conditions, initial conditions. And so our job as psychologists is to identify the relevant natural laws. So what does traditional psychology look like? Well, it's more like psychology. Cognitive science is very special. They're too complicated, and they have unique processes. So in response to that, cognitive psychologists are sort of free to dream up any sort of ad hoc, sui generis theory or concept in order to explain a phenomenon. And among these, you see a pattern, and where's the pattern going to come from? Well, a pattern will be explained by a pattern generator, a motor program, say, without feeling that as a loan of intelligence. And often, solutions to problems by circumstances. Again, let's take that line. Phenomena are to be understood in terms of law and circumstances. Let's forget the law and concentrate on the circumstances. So, for example, burying a lot of stuff in the head is really sort of solving problems through circumstances. The ecological solutions, so one more, solutions by algorithm and representation. The ecological view is more that perception, action, and related psychological phenomena are to be understood in an appropriately extended physics, a physical psychology. In fact, we have, I would say, one of the most eminent proponents of that in our audience, Gregor Scherner, who really does a lot of psychology by applying physics at an appropriate scale. So, for example, the physics of self-organization, if you want to understand where patterns come from, rather than burying patterns in memory and motor programs. Other approaches, trying to use laws that apply at different scales. For example, laws of flow, and where laminar flow becomes turbulent, might explain not only what happens in a pipe of water, but as people travel through a hallway that can't quite handle the flow that's appropriate. Physical laws that apply at multiple scales. And indeed, a final aspect of this is an enterprise by Robert Shaw and his colleagues called intentional dynamics that really tries to extend regular dynamics, the sort of physics of getting a particle from point A to point B, to information-guided dynamics, where now the deployment of onboard resources, metabolic resources, is dependent on information. All right, I'm not going to go through any examples of that. Let's turn our attention now to learning. From an ecological view, we'd like to emphasize that learning is change, that we want to educate our attention, right, what we look for over the course of learning. The more common metaphor for learning, of course, is the computer and the storage of information. So you're going to store information from the present and use it at some point in the future. And you're going to need to use it in the future, right? Because we know that the stimulus is ambiguous. Of course, if the stimulus is ambiguous, the only thing that could ever be in memory is ambiguous, but let's not go there. Part of this is rooted in our taking way too seriously the existence of a future that's got its own psychological processes, anticipation, extrapolation, prediction, a present that's got its own psychological processes, perceiving, and a past that has its own private theories of memory and recall and redintegration. Instead, and again, this is dictated by this idea of an ambiguous input. This starts you down the road of having to use all these complicated processes, and part of this ambiguity is rooted in this past, present, future trichotomy, to single out this one moment, the now, as the only moment that truly exists, and that you got to, what's going to happen in the future and what happened in the past requires something extra. Okay? Needs supplementation. The ecological view is that specifying information is available, and it can be about the future. It can be about the present. It can be about the past. Right? We're not going to tie information to being about some state, and then because it takes so long, it's always about the past because it was, it came in, 200 milliseconds ago. Not a problem, right? Information is spread out over time, and we're going to be looking for specificity. And now, from this perspective, your job as a learner is to learn to detect this information. So, the metaphor is evolution, right? Think about what happens in evolution. We don't have any complicated storage metaphors of, we remember what happened to the amoeba or the, prosimian, right? What happens over the course of evolution is that animals change, right? And what happens over the course of learning is that animals change. So you are not the same person that you were 50 years ago, no, 40 years ago, 20 years ago, with a bunch of memories, right? What has happened is you have changed. You're not just collecting things, you are altering the way you deal with information coming in. You are a new animal that knows better than you did in the past. Now, this concept of education of attention, or learning from an ecological perspective, can be approached and has been approached in two rounds. The first round was that of Eleanor Gibson, and the second is that of David Jacobs and myself. And I will confess to you immediately that Jacobs is the smart one here, the idea man, and I am his handmaiden of going and preaching the gospel to people and doing some experiments, but these ideas are primarily his. So, one important aspect of this, this theory in round two, the Jacobs and Michaels theory, in fact, departs somewhat from traditional ecological psychology. So I want to start by trying to pull us apart a little bit there. For Eleanor Gibson, and this is James Gibson's wife, and she was a developmental and learning psychologist of the pair, her view was that what you perceive is more direct. You start doing more direct perception. It's not more direct, it's more direct perception. Okay, that's how that should be parsed. That is, and think of an example of just learning to read X-rays, jobs that you might worry about, information people might worry about, or learning to distinguish fine wines, right? You detect more and more features. So Eleanor Gibson bought into the specificity of information, right? That the information is out there, it's available, and your job as a perceiver is to detect it and keep detecting more and more detail. Okay? And the basic idea, of course, in this specificity view is that the environment is related one-to-one to information, which is related one-to-one to perception. And because these are, you got two of these relationships, you can say perception is direct, perception is of the environment. So Eleanor Gibson started with that idea, and as part of the ecological view, she would go looking for information that people use, and again, demonstrate that over the course of learning, people detect more and more specific features, distinctive features. You come to see the distinctive features that distinguish that wine from that wine, or that kind of cancer from that kind of cancer. Now, Jacobs and I actually come at this from a little different view, not worrying so much about specificity in the way that traditional ecological psychologists have done that. In particular, we're kind of driven, this is not a philosophical assumption. We have been driven here by data, okay? That is to say that perceivers sometimes use non-specifying information. Take my word for it. You start to run correlations, you can show that there's perfect information out there, and then there's some very sort of low-level variable that perception is, you can just show there's a perfect relationship between those. So Jacobs and I have backed away from the idea of information being specific to the idea that the variables that one might use constitute an information space. Okay? Not a single variable. This is for some task, let's say perceiving the age of a head. There might be a space there. And at some time, a perceiver might be in a particular location. And what learning is all about is traversing the space to a better location. Okay? So, given consequences, you move through the space and start using a better locus, something that's informing you more appropriately about what the environment is like. Importantly, we argue that this movement through the space is guided by information. More strongly, that you are pushed through the space by information. And so, we really need, though, in order to understand that, to distinguish between two kinds of information. One is the information for perception, that which you are detecting as you listen to my speech, for example, and that's going to be distinguished from information for learning. Okay? And my main focus in what's coming up is to try to make this concept of information for learning clear to you. And I think, in fact, that this might be the most helpful, perhaps a helpful concept for those of you that worry about machine learning and robots. So whereas the strategic commitment for traditional ecological psychology. I've got traditional psychology and now traditional ecological. But for regular ecological psychology is find the variable that specifies when to start your baseball swing, or whether to run forward or backward, specifies whether to run forward or backward catching balls, or how to drive a car or land a plane. Whereas information for learning is what David and I would be looking for. We don't care if it's specifying information that you use in perception. What we think is you get pushed to using better information, and that you're very opportunistic in your use of information. And that's the level at which we want specificity, that you get pushed appropriately through the space to detect useful variables. All right, now I'm going to try to make these points clear in describing a few experiments. One is learning to perceive magnitude. So this is a magnitude estimation task. And I take back everything I said about, oh, you got to do perception and action together. Yeah, you really should. And that's a problem with this study that I'm going to present. But it offers a nice way, I think, of understanding this concept of information for learning. So, and it's a little complicated, so hang in there with me, please, because I think you'll find it worthwhile. Here's the task. There's a hammer of sorts that's presented on a computer screen, and a subject in an experiment is asked to identify a kinetic property of this hammer. And that kinetic, there were actually three conditions. Some subjects had to report the mass of the hammer, estimate the mass of the hammer. Some had to report the torque, and some had to do sort of moment of inertia, although we didn't use that phrase. The way the hammers differed among each other were the radius and height of the hammerhead, and the length of the handle. And we started out by just showing a handle of 30 centimeters on the screen, handing them a 30-centimeter handle made out of solid aluminum, and that was going to help them scale things. So you're holding this 30-centimeter rod, and now a hammer appears, and you have to say, let's say you're in the mass group, imagine that the hammer weighs, the rod weighs 10. If this weighs 10, what does that hammer weigh? And then you make, or some subjects make torque judgments. Imagine holding it at the end. If this pulls down, 10, how much would that hammer pull down, et cetera. All right, then the paradigm was we'll test people just from the get-go, and then give them 3 training blocks. What happens in a training block? You say that hammer's a 13, and I say no, it's an 11. Okay, that's all, just verbal feedback. What we find is that people learn. Okay, so far so good. But obviously our interest here now is in the information space. So what would be the information space? Now we're going to give up sort of on single variables and say there's a space of variables. Now normally you'd want to do this in terms of optics, but I'm just going to do it in terms of hammer characteristics because there's sort of a one-to-one mapping there of hammer characteristics and optics. And I'm going to make the information space be the surface of a sphere. Okay? And this is going to be the important part of the sphere here. And the sphere is set up so that if you're just using radius, you'd be in this location. If you're just using height, you'd be in this location. Just using length there, all 3, etc. Okay? Now, if you want to make mass judgments, the area to be used is this. This is a contour plot representing correlations between how good the information is at that point and the actual to be perceived mass. Right? So from a dimensional point of view, what you have at that little spot is r squared, so basically the volume of the hammerhead, r squared times h times length, to the 0, so length is not contributing. So that's where you want to be to perceive mass. Where do you want to be to perceive torque? Well, you want to be up a little higher where length is now contributing. Dimensional analysis of that would be that torque is going to be a function of the radius, the height, and now the length. And where do you want to be in that space if you perceive, if you want to perceive moment of inertia, you want to be up a little higher if you want to report moment of inertia, namely where the L term is now squared. Okay, so there are our best locations. Now, what do subjects do? So for the mass group, that's where they want it to be, in that circle. And what we find is, at the beginning, the subjects are kind of spread around. And let me capture those subjects with just an ellipse carrying the error. So there's an error ellipse from what happens on block 1, the pretest of this experiment. And block 2, we see now a convergence to the use of better information. Torque group, similar. Convergence, a large spread that gets smaller, and the inertia group, a large spread that gets smaller. This looks a little weird, but it's kind of weird the way Greenland is weird, you know. Stuff up there gets spread out. Okay, so now what we have captured there is, now that's the information for perception. We still haven't touched on the information for learning, how you get pushed around. We have seen that people get pushed around, and now the question is, can we predict or explain how and why they get pushed in the way they do? So to distinguish this information from learning from information for perception, the information for learning is just these two angles would be that identify where you are on the sphere, right? So perception is going to be a function of whatever those two angles are, and though the variables there are free to, at any one location, right? You've got different radii, you've got different lengths, you've got different heights. So being in a place in that space is using a particular variable, using a particular combination. Okay? And now, over learning, those angles are going to change. And so now what we're looking for is a lawfulness of those changes. What kind of information, and this is sort of the more formal definition of the information for learning, is that information that drives the movement through the space. What do we want this information for learning to be like? What characteristics ought it have? First of all, to be useful to us as scientists and to, and to the subject, it's got to be observable. It's got to be something we can point to and test. It's going to need to specify the change that you need to make, right? It's got to tell you how to move. My working hypothesis is that it is covariation of error and information variables that you can actually measure with correlations. I'll give you an example of this in a moment. And it's represented as a vector field in the information space. All right, let's try to get an intuitive example of this. Let's say you're asked to make torque judgments and you are sitting at that spot. You're sitting in the mass spot, right? What's going to happen? Length increases, torque increases, but since you're ignoring length, your judgments stay the same. This is other things being equal. If we now plot the errors that you make as a function of length, this perceived property, we see that there's a correlation there. The short version of this is going to be, you've got to get rid of that correlation, right? That suggests that there's something missing or wrong in your variable use. And so let us now measure the correlation and say, in this case, it's going to be -1. Now, your job then as a perceiver is to go upward in the space. It's going to be minus the correlation. So as you see here, you should be going upward in the space. We can repeat that for somebody who starts in the right space. What's going to happen is length, torque, and now the judgments are proportional to torque. So we're going to have an error. You can have an error, but it's not going to change as a function of length. And you have that which says you're in the right region with respect to the horizontal dimension. So don't change in that regard. Similarly, if you had a torque judgments coming from someplace up more like moment of inertia, you were going to be kind of overusing length. And you know, this is varying basic, whoops, this should be 16. We're varying as a square. And now we plot that correlation. You want to get rid of it, so now you go down. Okay, so you would do that exercise. So we're talking about being in some spot. We've just determined an arrow that says go down. You would repeat that for another dimension and take the resultant and put that as a vector. This is the information for learning at a particular place. It's how you should be moving through the information space if you happen to start here. And that's what we say, you just happen to start someplace. And now we can repeat that exercise for the whole field, and we end up with this vector field in the information space where the magnitude and direction of the vector sort of point you in the right distance with a certain oomph, if you will. So that's the one. That's the torque vector field that you create computing those values that I just described. And an analogous one for mass, again, you're down around 0 here, here, and then a very different one for moment of inertia. Now, the formal hypothesis is that if you have got the right vector field here, the vector field that you see from your subjects, namely, first they were here, then they were here, then they were here, this guy started here, and then he was here, then he was here, those should be one and the same. There should be a symmetry between your information for learning and vector fields and the vectors that capture a subject's movement through the space. If they don't agree, you haven't got the information. But if they do, then perhaps you do have the information. And I'll just, this is a little complicated to figure, but it basically, it compares, let's just take one point. Here's the observed movement of a particular subject. He started way up here, and he ended there. Now, the information field I just described for you would say, oh, you should be going there, right? So what you would want is substantial agreement between the solid arrows and the lines that end with an asterisk, okay? Nothing's going to be perfect, of course, but that's the agreement that you'd be looking for. There's another line up there, in which is, you know, if the subjects if the subjects were following a gradient, you know, let me try this spot, let me try this spot, oh, that one's better, I'm going to go that way, right? That's the prediction that you would get from that, sort of following the gradient of performance. Now notice this is not a search procedure. You are at a place, and you're using a variable, and that's generating information right here, right now, that will yield a vector. You don't have to be comparing things. You're here, that you generate responses being here, you get feedback being here, that creates a vector, now go there. Okay? So it is not a search algorithm. All right, let's turn our attention to a second example. learning to perceive length in dynamic touch. So somebody's shaking a stick behind a barrier, and you ask the subject to report a certain characteristic about it, say its length. And what the subject will do is to adjust some marker, in this case that light blue square, and adjust it to some other position, and then we will either give them feedback or not. And the standard paradigm, again, see where they are to start with, give them some training, and see where they end up at. What's the information space? I'm going to go through this a little quickly. Previous research has suggested that some previous research has suggested there are two variables that are relevant to this task: the first and third principal moments of inertia of the wielded object. So we can make a space out of those variables, where a certain place might be just reliance on, I can't do this fast enough in my head, especially if I want to do it fast. So along here you have various ratios and products. Let's not worry about the details. And certain places there are stimuli. Some of them are fat pipes and rods, steel, aluminum, PVC. And we can say, how good would your length judgments be at any place along this line? That it's easy to compute. I was going to take you through that, but I won't. Take my word for it. Those are examples of where you want to be or what kind of performance you could achieve at each locus on this information line. So we have our information space here, notice, is just one-dimensional. Again, pretest feedback, and now if we see what a particular subject might do, this particular subject started in this locus, performing fairly poorly. On the next block of trials, about the same. Now he's getting feedback, he jumps up to this position, and then on block 4, he goes up there. Okay? And we can capture that as vectors, right? Of how the subject moved. So what our information space would want to do for us is predict those vectors. So over subjects, we observe this kind of movement. Okay? So that's the to be predicted phenomenon of movement through the space. I just want to stop at this point and compare different kinds of theories. So we got two variables that we might be using. One kind of moment of inertia and another kind of moment of inertia. And computational theory is happy with 2Qs. But I want to disabuse you of the 2Q theory and say there are other ways to think about this than just taking Q1, Q2, and doing something with it. So the traditional computation theory would be happy with 2Qs and would say that you weight them based on experience. So what you have is some recipe for these moments, which you put into your stew pot or behind your stew pot. And then over the course of learning, you change the recipe. This is the sort of a standard view. Well, the direct perception view and direct learning view would be what you need to learn is how to shake this stick so as to be in a particular place, to be in the space you want to be, in the space where length is specified. Okay? The idea is that if you rotate the object properly, the resistance to rotation will specify length. Okay? So direct perception entails wielding appropriately, and direct learning entails learning to wield appropriately. Okay? Which is a very different sort of idea from take 2 cues and combine them mentally. your exploration is combining them. And indeed, we observe that over the course of learning, there are systematic changes in the kinds of exploratory characteristics. My time is running out, so I'm going to kind of skip ahead here. I cut half of my talk yesterday, but I didn't cut enough. Again, we came up with a covariation of error and mass, and now ask, again, to these two vector fields, that describing learning and that describing a candidate for information for learning, do those two match one another? The correlation was quite modest, but at least there was a correlation. But that's okay. I mean, if you get the information, great. If you don't, keep looking. That's where the commitment is. We'd say there is information there that's pushing you through the space. Okay, we've also applied this to learning fold balancing, where we make a space of fractional derivatives and calibration constants and discover that there's where you want to be. And through simulations, there's where you want to be. And then over the course of thirds of an experiment, we see again subjects converging on that. I don't have a good characterization of the information for learning. Here I'm just really trying to emphasize information space and changes in information space. And finally, we're also doing a bimanual coordination task now in which we're applying these concepts. So let me summarize the key ideas. The ecological approach is very different from traditional cognitive science in its emphasis on first animal-environment mutuality. What's that going to do for you? It's going to help you solve problems from the outside, okay? Now, traditional ecological psychology had the problem that was being solved from the outside was perception, right? Here's information that specifies what you need to perceive. But now, in fact, we have something even richer. Here's some information that will drive your learning. Specificity of information, again, there's a departure for traditional psychology. That specificity is at the level of perception. For David and me, we're happy if people use, especially novices, use lower order variables. Perception is opportunistic. Let's take advantage of, special local circumstances. But what we want specificity for is to help you to find information, to push you to find information that's appropriate for guiding your activity. Again, the emphasis is on guiding activity, which not only is about execution, but is also about creating information, as we saw in exploration. That perception is direct. We've got good information out there. Our job, both in terms of perception and in learning, is to pick it up. Not store it, not embellish it, pick it up. And it's going to be happening and helping us over many time scales, right? The perceptual time scale, the calibration time scale, the learning time scale. Let's not get hung up on this past, present, and future trichotomy as if those are real things that are sort of the starting point of our metaphysics. We want to exploit, insofar as we can, physical laws, and then this idea of changing with experience as opposed to storing. The direct learning part of this, the key ideas, let's not think about perception and action just in terms of single variables, and that's your job as a scientist, find this variable, right? We're going to do things differently. We're saying, hey, here's a space that contains the variable that perceivers use, and that learning is traversing the space, and that traversal is not a matter of search, trial and error. It's a matter of detecting information that pushes you appropriately through the space. And finally, that we're going to characterize that as a vector field in the information space. And the key that ties it all together is that when you have the right space, the vectors of movement through the space that you will see in your experimental subjects or in your computer applications would be the vectors of the information space. And of course, you can make it like that as roboticists and information theorists. And again, if a particular variable, information for learning doesn't work for you, no problem. We just don't give up. Science is hard, and then you die. No, one keeps learning and rejects. If you're not accounting for the traversal through the space, then we would suggest that you have to look elsewhere. Okay, I think that's it. Thank you for your attention.